Okay, so now for question 2. So question 2 was quite a difficult question. You'll always see that your first question will be multiple choice, your second question will be Newton's laws. So this one comes down to Newton's laws, and you can usually determine what the questions are going to be based on the first question in your question, which is a theory question. So here we have a heavy metal container with a load of mass 1,000 kilograms. So that's one, is pulled up a 30-degree slope by a counterweight that is sliding down a 60-degree slope on the other side. So that slides up, that's going, slides down, that's sliding up. And so the first question asks, give a definition for maximum static friction. So what is maximum static friction? Well, first of all, static friction is the frictional force that an object experiences while it's stationary. So maximum static friction is the frictional force that an object experiences, the maximum static friction that an object can experience. So maximum static friction is the maximum force to apply before an object starts to move. Okay, so it's the maximum force that you have to apply before an object starts to move. So when an object is just on, so let's put an object, for example, just on a horizontal slope. What is the static friction experience that it's experiencing? Well, nothing, because there's no incentive to move. There's nothing that causes it to move. So the moment I start pushing on this thing, now it's experiencing friction, because now there's an incentive to move. There's something that is trying to move it, but it's not moving. What is causing it that it doesn't move? Well, it's friction. Now the maximum force that I have to apply before it starts moving, that's called static friction. But I'm not going to reteach the theory. So there we go. How does the kinetic frictional force compare to the maximum static frictional force? Write down larger than, smaller than, or the same as. While kinetic friction will always be smaller than. Okay, so kinetic friction is, this is question 2.1, 2.2, smaller than. And these are all theory questions. So next question, when the heavy container reaches the top and is offloaded, the container itself is used as a counterweight to pull up the next load. So basically what happens is this container is being pulled up. The combined mass of this container is 1,000 kilograms. When it gets to the top, it's offloaded, and the container itself becomes the next weight that pulls up the following mass. Okay, so the first question, coefficient of kinetic friction, is that draw a force diagram to show all the forces acting on the load as it's being pulled up. Okay, so now this force is being pulled up the slope. What are all the forces acting on it? Well, the two that you can always get immediate marks for is one that goes straight down, a force that goes straight down, and that's just weight. Okay, just a straight down force. There's one mark. The next one is one that is parallel to the surface. Not parallel, perpendicular to the surface. And this one, nobody got right. It blew my mind. No one, I don't think anyone did. Maybe there was one person. No one got it right that there's one force that is perpendicular to the surface, and that's the force that the surface applies, the normal force. So you can either name them or you can label them. So let's just name them the normal force. Then there's a force, and this force doesn't always apply, it depends. Is there a force being applied? Yes, there is. There's a force being applied. This object is being pulled up the surface, so there's applied force. You can either use a T for tension, or you can use FA, or you can write applied force. Okay, applied force, whatever. Okay, and any other forces? No, nothing. No, in this case there is another force. There's friction, because they say there's kinetic friction, coefficient of kinetic friction. There will be a frictional force, and the frictional force is always in the opposite direction as motion or applied force. So if the applied force is upwards, then frictional force will be downwards. If the applied force is down the slope, the frictional force will be down the slope. The frictional force will always be in the opposite direction as the applied force. Okay, or actually as the direction. Usually it's opposite applied force. There's a few exceptions, but safest bet is in the opposite direction. So one very common mistake is people just did this. Okay, so and for this and naming it, you'll get 3 out of the 4 marks. Why? Because your normal force must be perpendicular. So this is a very common mistake. Some people put in the components of the vector. There's one component there, one component there. That's not necessarily. It's really simple drawing force diagrams. A weight that's downwards, find the surface. If the surface is at an angle, then just draw a 90-degree vector to that angle. Name it normal force. There's always a normal force if an object is on a surface. There's always weight downwards. Always weight downwards. A lot of people didn't get that mark. If there's an applied force, well, just what direction is the force being applied with? If is there friction involved, then there's a frictional force. So really very simple, and it's shocking that I think maybe one person got full marks. Okay, what is the applied force required on the load to cause the load to move up the slope at a constant speed? Okay, so now I want to let this thing go up the slope at a constant velocity. Okay, so for constant velocity, we need our net force. We need net force to equal 0. Okay, because force is mass times acceleration. Net force is mass times acceleration. Another way you could have done it and saying, okay, acceleration, because this is Newton's second law. Acceleration is net force over mass. Okay, so in other words, if it's going at a constant velocity, it means acceleration is 0. Okay, so when you see the concept of constant velocity, just immediately put in net force is equal to 0. That's just basically what it means. There's no net force acting. The moment there's a net force, there's acceleration. When there's acceleration, it doesn't go at a constant velocity. So net force is equal to 0. Okay, so what does that mean? Well, it means when I add up all the forces must equal to 0. Okay, and these forces added together must all be in the same direction. So let's have a look. So this thing is traveling along the slope. So what is the net force? It's all the income forces. Well, what's an income force? A force that helps it to move. What force is helping it to move? Well, there's tension. Okay, that's pulling it up the slope. What other force is helping it to move? Well, nothing. Okay, for one, friction is not helping it to move because the friction is in the opposite direction. Normal force is not doing anything in this case except helping it not to fall down. So normal force is 90 degrees to the motion or the direction of motion, so it doesn't have an effect. Weight is having some effect. A part of the weight is weighing down on the surface, so the normal force counters that part, but another part of the weight, this component of the weight, is pulling it down. So both weight and friction is in the opposite direction. So if we go and we say, well, net force is therefore the tension minus the component of the weight that is parallel to the surface minus friction, and all of this must add up to 0. So basically what it means is that the tension in the rope, the force that I'm pulling it up with, must be equal to the force that is weighing it down the slope and friction altogether. So we have formulas for these. This is just weight. which is mass times gravity times sine of theta, the angle of the slope. Friction is just, and this is kinetic friction because it's moving, so it's the kinetic frictional coefficient times mass times gravity times cos of theta, okay, is equal to 0. And now I simply substitute. It was really a straightforward question. So if I just plug in all my information, my angle is 30 degrees. Okay, my mass is 1,000 kilograms. My gravitational coefficient, and what am I trying to calculate? I'll just go back, make sure I draw force on what is the applied force required. Okay, and that's this T value. Okay, so I just say T is, mass is 1,000 times 9,8 times sine of 30 degrees minus mu was 0,1. Let me just confirm that. 0,1, yes, times 9,8 times 1,000 mass, sorry, that should be turned around, times cos of 30 degrees. Is equal to 0. So obviously I'm just, since both of those values are going to be added on the other side, I'm just going to add them together. So I've got, what I could do is I can just take out 1,000 and 9,8 as a common factor. And so I have sine of 30. So 30 sine plus 0.1 times 30 cos. 30 cos, okay, is equal times 1,000 times 9,8. Okay, there we go. 5748,7. This is what I'll get here when I subtract that, so it would be minus, and when I put it to the other side, 5748,70 newtons. Okay, confirm that. 5748.70 newtons, and up the slope. Always remember your units and direction. So I don't know, I don't find this to be very complicated, especially if you just keep in mind that you're working with Newton's laws. Newton's laws basically come down to using that your net force is equal to your mass times acceleration, and your net force is the sum of all the forces. Income forces, I call it income forces. It's not really called income forces. I call it income forces because we're working with net force. So income is forces that help me move, expense forces are forces that rob me of movement, so forces that work against my motion. And so I sum up all those forces. Some are positive, some are negative, depending on whether they help me move or not. Mass times acceleration in this case was super easy. They could have said I wanted to accelerate up the slope at 2 meters per second, and then A would just be 2. In this case, it was 0. It was constant acceleration, so it was 0. Really straightforward. When you practice these things, it's the same principle over and over. Now the next one, and so you see 4 marks is roughly, in this case it's not a lot of work for those 4 marks. Okay, so when the load reaches the top, what is the maximum mass that can be offloaded so that it's able to act as the counterweight, exerting the force in question 2.3.2 on the next 1,000 kilogram load? Okay, so if I go back, is now when I get here, I want to offload this thing so that when it's on this side, when it's empty, it is able to apply this force that we have here. It's able to apply that force to the next load. Okay? So let's quickly draw our our force diagram here. So we want in this direction, we want a frictional we want a T equal to 5748 newtons. That's what we want to be able to apply. In other words, that's what's going to pull us in this direction. So the tension upwards and tension downwards is the same. In this case, we still have a downwards force, and we have our normal force perpendicular to the surface, and we've got another frictional force, this time in up the slope. And the reason why up the slope is because this thing is now going to go down the slope. So this time I want my net force is still going to be 0. The sum of all the forces is now, this time, tension, the T, is not helping me to move, it's actually pulling me back. I would slide down quicker if I didn't have the tension in this rope. Okay, so what is helping me to move this time is weight. It's now gravity letting this thing pull down. So this time my positive force is the weight that's parallel to the surface. What's weighing me down is my tension in the rope, as well as the kinetic friction involved here. That's equal to 0. So this time I just want to know what weight do I need in order to be able to do this. Well, now the weight parallel to the surface will have to be equal to the tension in the rope and the frictional coefficient, or the frictional force in this case. So this is this 5748,70. That's what I need in order to pull up the next load at a constant rate, plus, and then I need to overcome my own friction as well. And in this case, the friction is, okay, so on this side we've got mass times gravity times cos of 60 degrees. And on this side, and we have the gravitational constant. On this side, we have, the problem is we don't have mass. So we have mass times, I suppose I should have left this that side, but okay, doesn't matter. Well, it does actually, it makes this a little bit more difficult to, let me just write this out again. I want to keep the unknown on the left-hand side. So what I mean is I want to keep it like this, because mass is unknown. So mass times gravity times sine of theta minus mu, okay, mass times gravity times cos of theta is equal to 5748,40. Was it 70? 70, sorry. 70. Okay, and here now just substitute my values. Mass, don't put in 1,000 kilograms. This thing isn't 1,000 kilograms anymore. The whole point is I want to know how much mass do I need. So how much can I offload so that my mass is still enough? So I don't know. Mass is the unknown. Mass is the unknown. Gravity is 9,8. Sine of 60 degrees this time minus 0,1. Mass is times 9, mass is unknown times 9,8 times cos of 60 degrees is equal to 5748,70. So now we just take out mass as a common factor. So mass can be taken out, and we're left with this minus that is equal to 5748,70. So let's calculate that. So 9,8 times 60 sine minus 0.1 times 9,8 times 60 cos is 7,997. Just all that. So it's 7,997, what? Don't round off yet. Only round off in your final answer. And so now I'm going to take this and divide by that number. So 5748,7 divided by that value is equal to 718,85. 718,85. Is that correct? 85, there we go, kilograms. That's how much my object, the mass of my object. Now I want to say, well, how much must I offload? Well, originally it's 1,000 kilogram. So I can offload 281,15 kilograms. I just subtracted it from 1,000. I hope I did it correct. Looks like it. Okay. 281,15 kilograms. That's how much I can offload in order to pull up the next load at that constant rate. Okay, the previous question is an example where the weight of one object can be used to lift another object. Describe another practical use for gravitational force. And so this is simply a way in which now we want a practical use. How can you use gravity in your favor? And there's loads of examples of using gravity in your favor. So for example, by doing exercise, that was one example a student gave, is doing exercise. When you pull yourself up against some pull-up bar, you're using gravity for a practical purpose, because gravity is pulling you down, you pulling yourself up, so you're building muscle. So it says describe. So you can't just say exercise, you must describe it. You say, and in more or less the same words that I used now, saying that by using gravity you can do exercises by pulling yourself against the gravitational force, something like that. It just makes sense on how you're using gravitational force. You can say, for example, that electricity can be generated from a waterfall, because as the water is falling, it can turn turbines, and that causes that can generate electricity from a waterfall. Another example, not even a waterfall, even just water in a river flowing. Why is the water flowing? Why is it flowing? Well, it's flowing because gravity is pulling it to a lower level. So it's not even just waterfall, but a waterfall is an example. Other example is satellites in orbit. Satellites stay in orbit because they are falling to the Earth. And if I can just show you that, because I don't think people really know this. But a satellite is, let's say that's a satellite. The satellite is falling to the Earth, but it's also in motion. Okay, it's in motion, there's no frictional force, so it's the whole time in motion. So as it's trying to fall to the Earth, so you can now, as it's falling to the Earth, it keeps falling in that direction. Okay, because it's moving in this direction, it's falling in that direction, so the net vector is in that direction. And that's true anywhere on this spherical object. So that's why it is continuously falling around the Earth, basically. So that's another example. There's loads of examples if you just think about stuff. I think practical use of gravity, it's not really a use, but can you imagine if the effect on our internal organs? If we ate and food didn't go down our throats, it would be more difficult to swallow. There's loads of good examples of gravity in practical use. Okay, so that's question 2. Let's just quickly look at the time. I like to look at the time to give you an idea of, so let me just get the time up here. It took 24 minutes to do this question up to this time. That's with explanation. So when you have 18 marks, you must spend 1.2 minutes per mark. So we should have finished in 21.6 minutes. Now, obviously, I spent a lot of time talking, giving extra examples, etc. So I spent an extra 3 minutes on this question. But just to show you how you should spend your time on a question as well, and that there's more than enough time there should be enough time if you know your work. So thank you for watching. This was question 2. Question 3 coming up.